Good. So the summer term is devoted to machine learning methods in neuroimaging. So in the summer term, I switch around what I teach quite regularly. So in the winter term, we always do something related to, in a way, classical statistics and the general linear model. In the summer term, we have seen courses on random field theory for neuroimaging and multiple testing correction in some depth. We have seen courses on biophysical modeling, so stuff that you might know under the term dynamic causal modeling. And some time ago, I think, when was the last time that I taught that? Like in 2015 or so. And I think also when I first started this whole thing, the summer term was usually related to machine learning methods. I haven't taught machine learning methods for some time because I use them in my research, but not as much as other people. And so it's not something that is too closely related to my research, but now I thought it would be good at one point to talk about them again, and also update a little bit myself on this, and then also my teaching materials. So today we're going to start first with an introduction, which is happening now, and then hopefully later, not hopefully, but definitely later also with some stuff on optimization. So when I tried to put together this intro lecture, I, of course, would have liked to start it with kind of a nice definition of what machine learning is. So something like machine learning is the learning of knowing how to interact with the world by machines, or machine learning is a set of methods that allow computers to analyze data or something like that. And there are these definitions around, but whenever I read one of them, I feel like, yeah, one can say that, but somehow it doesn't really describe what I have learned about machine learning, because it doesn't quite match. And so I really had the problem of coming up with a good definition of what machine learning should be. Now, what I'm quite clear on with respect to machine learning is that machine learning involves these kind of steps, which you might have seen before, for example, under the label of statistics or under the label of science by me, because I label this thing usually science or statistics. So somehow machine learning, like statistics and science, involves the analysis of data. And what machine learning then is about, and what is being discussed, is how models for data are formulated. So there are different model classes in machine learning. So for example, support vector machines, or neural networks, or Gaussian models, or variational autoencoders. These are all different mathematical models. And then a big part of machine learning is then actually to learn parameters of these models, or to estimate these models. So this is where data then informs the model. And then, of course, also one part of machine learning is to evaluate models, for example, by what you might have heard about as cross-validation, or what you have heard about as model comparison, or Bayesian model comparison. So from my perspective, and this is already then what the main message would be, and I'm trying to kind of give more and more on that, is that machine learning is not different from statistics or from any kind of data science. It's essentially the same thing, and exactly the same problems are addressed. However, there are differences in terms of the models and the methods that are being discussed. for example, machine learning as compared to what you would call statistics. So for the data science, for the one data science student, this is something that I also showed in the introduction to data science. So for me, data science is kind of this union field of statistics, machine learning, and artificial intelligence. And in each of these subfields, if you want, of data science, you have essentially the same problem, but certain things are more emphasized and other things are less emphasized. So in statistics, so this also relates to essentially what you did in the winter term, because the general linear model is a typical thing that people will call statistics. You're dealing with probabilistic models. You all know that this was about a normal distribution with some mean that was given by the product of the design matrix and some parameters. Statistics in general is a lot related to, or tries to figure out justifications for procedures, and in this scenario looks at questions of optimality and asymptotics. So that will be a little bit clearer for people who study data science, because there, when we did the statistics, we emphasized these optimality and asymptotics a little bit more. And if you want, it's a little bit, statistics a little bit more on the big picture science philosophy field. In machine learning, if you want, and if you open machine learning books and so on, the probabilistic aspect is not necessarily emphasized. So you have can read machine learning books that don't really give profound introductions to probability theory first before they start talking about machine learning, although the good ones actually do. Then machine learning is often interested in classification procedures, specifically based on high dimensional data, which is one thing that we will also emphasize. Then Bayesian models, at least in certain parts of the machine learning community, are a little bit more popular than Bayesian models in statistics, where if you have a typical statistics old school department or some biostatisticians and so on, they will be pretty frequentist oriented. And then, of course, in machine learning, you have a lot of stuff that is somehow application linked. Of course, statistics is also application linked, but machine learning, specifically because machine learning is also happening a lot in these kind of conference style community discourse, you find a lot of novel applications of this to that. And then, of course, since 2015 or so, artificial intelligence has joined these kind of statistics, machine learning, data science fields for real. So artificial intelligence kind of got into or was popular at certain points and then was not popular at other points. And since deep learning came around, so the second rediscovery of neural networks, since deep learning came around in around 2012, artificial intelligence is also somehow there, and specifically the link between deep learning and reinforcement learning is quite big in artificial intelligence. So from my personal perspective, and we'll see a little bit more about this, I see statistics and machine learning essentially as the same thing with some different emphasis. From my perspective, artificial intelligence is a little bit different in the sense that in artificial intelligence, the focus is more on agents, which also act on the world. So they also act on data. So they determine what kind of data they actually see. And this is something that I don't, which is not that emphasized in statistics. So in artificial intelligence, things typically act, and you understand things as acts. If you really think about it in statistics, for example, hypothesis testing, a proper way to introduce hypothesis testing, or even Bayes estimation, is also to understand that from a decision-making viewpoint. And then this is again very close. The focus is much more on inference in statistics and machine learning, and more on action and optimizing interaction, artificial intelligence, if you want. There is, in terms of how people talk about things, there are different words in the different communities which mean the same thing. So in statistics, one usually talks about data. In machine learning, people like to talk about training data or training data patterns or whatever, but the meaning is just that's data, that's acquired data. Statistics, you know that we learn, or we estimate parameters. So parameter estimation, for example, beta parameter estimation was a big thing in when we talked about the general linear model. In machine learning, parameter estimation is usually called learning or training. Yeah. So machine learning, I think one can also call statistical learning, and statistical learning essentially is parameter estimation. So you use data to estimate parameters. So that's what I showed earlier in terms of model estimation. Yeah, so training some neural network or training a support vector machine means learning the parameters of a neural network or a support vector machine based on training data, and learning parameters just means estimating parameters. The difference is usually that one doesn't consider the probabilistic implications of learning and training that much. But if you actually look, for example, at what Frank Noé is currently teaching in his deep learning course, he also has a session on statistical estimation theory, and he's discussing things like bias variance trade-off there, which we also did in statistics for data science, because it's a statistics thing. But for some reason, like I already said in statistics for data science, for some reason this bias variance trade-off also made it into machine learning, while a lot of other concepts from statistics didn't, which is a little bit weird. Sorry. Anyway, that's estimation versus learning and training. Frequentist inference, so this typical thing that you know from undergrad statistics and also from what we did in the winter term. So t-test, p-values, maybe simple linear regression stuff. Simple linear regression also happens in machine learning, but p-values and t-tests, they really seem to be absent from machine learning for whatever reason. Usually so frequentist inference is not big in machine learning. What is actually quite big in machine learning is Bayesian inference. So probabilistic modeling is big in machine learning, maybe even bigger than in the statistics communities. So one thing that drove me first to machine learning was that they were doing a lot of more probabilistic modeling in terms of Bayesian inference than what I knew from classical statistics. And so that's the same Bayesian inference as in statistics. So there is only one probabilistic modeling framework called Bayesian statistics, and that's the same in machine learning and statistics. And then there are maybe more subtle things like that features that in machine learning that are used to predict data are sometimes called covariates in statistics. That one I actually would have to discuss a little bit more. But so there's a lot of this stuff where you have terms in, and this one I want to emphasize here. There are a lot of terms in machine learning that have a direct correspondence in statistics and actually mean the same thing. For some reason, or at least for me, it always feels like in machine learning they are a little bit cooler. So and this is also what, of course, drove me at first more into the machine learning direction than in the statistics direction. So it's a little bit cooler to talk about training data and training a support vector machine than to estimate the parameters, which sounds a little boring, but it's the same thing. And if you if you're not, so you should approach anything that you read in machine learning under in the mind frame of this. They are just trying to tell me about doing statistics, but in more relatable words, if you want. Yeah. So that's about nomenclature. Does anyone have, do you want to comment on that? So is there anything that you have previously learned about the difference between machine learning and statistics, or the commonalities that somehow contradicts this, or that adds something to that? Anyone? No. Okay. So in terms of machine learning and its history, because I think in the general public, machine learning seems to be in a way a modern thing. And if you would ask politicians in Germany right now, they would usually answer that artificial intelligence has been invented in 2015 and machine learning at the same time, or they don't know what machine learning is or something. But the thing with machine learning is that it's also, of course, has a long history, maybe actually not quite as long as statistics. And the main reason for that being that, of course, machine learning relates to computers. So you can also call machine learning computational statistics, because machine learning really only started once computers were around. And one thing that I found via Wikipedia on the kind of origins of the term machine learning is this paper by Samuel from 1959, which is called Some Studies in Machine Learning Using the Game of Checkers. Checkers is Dame in German. So essentially, he builds a checkers computer, like a chess computer, but build it for checkers. With some rudimentary computer that they have at that time. And obviously in the title it says machine learning. And I find this quite interesting to see the term machine learning in this context, because you might know that what the latest developments in machine learning or AI are concerned with is actually also games, right? So if you know the DeepMind stories and the hype on deep learning, deep reinforcement learning, then you know that they applied their algorithms to Atari games, so computer games from the 80s. And this kind of link between video games, or let's say games at least, and artificial intelligence slash machine learning has been around since kind of the inception of the machine learning field. I didn't know that, so that I found interesting. But again, the point here is that machine learning didn't just start like in the 2000s or something, or when really powerful computers, or let's say the computers that we have right now were around, but it started as soon as there were kind of computers. So this is a little bit more of a historical timeline of the development in machine learning from this very nice book by Efron and Hastie, which is called Statistical Inference in the 21st Century or something like that. And they discuss this whole interplay between statistics and machine learning. And they also give for everything essentially a nice historical perspective. And so the story of machine learning then definitely can be traced back to any kind of data analysis before the beginning of the 20th century. You might know things like Kalman filter, which is also popular in machine learning, but this has also been discussed already in 1800 whatever by some Danish astronomist and so on. I started here with what you all know, namely the classical mathematical statistics, which started out in the 1920s. So this relates to all of the stuff that you know from undergrad statistics, so Fisher, hypothesis testing, students' t-tests, and so on. So that was 1920s statistics, non-in-person hypothesis testing. Of course, at that point, largely, at this point, without the help of electrical computers as we know them now. But then after the Second World War and with the beginning rise of computers, machine learning, as we've just seen, proper started, and one early thing in there were early neural networks referred to as perceptrons, which actually originated kind of in psychology. So that was kind of in the 1950s, and then in the 1960s, Bayesian methods, specifically with respect to sampling procedures, so MCMC, with the development of Metropolis Hastings algorithm and so on, started to become more interesting. Then there was this AI winter, which followed after showing that the perceptron cannot really solve exclusive OR problems. And then for some time, artificial intelligence and machine learning went out of fashion. And of course, everybody's afraid, or not really afraid, but in machine learning, in the AI community, people are of course aware of that and always fear a new AI winter, although it's definitely not looking like this at this point. And I think it's also unlikely because unlike the 70s with digitalization and so much more digital data, I think it's very unlikely that data analysis procedures like machine learning and AI will go out of fashion again, because we just have too much data these days, and that wasn't available in the 70s. Then in the 80s, you might know that in cognitive science, connectionism, so again, neural networks, became more fashionable again, and back propagation. So an important component of training neural networks was reintroduced and caused some interest for researchers. And then I think, or at least from my perspective, then really in the 1990s, machine learning started to take off. One part related to the discovery of support vector machines in the West. For some reason, I've now forgot the name of this guy. Franziska, do you remember the name of the guy who started support vector machines?
Right now.
Bernhard Schulkopf?
Nee, not Bernhard Schulkopf. That's very nice. He would like to have been the person who started support vector machines, but he was not the person. He actually studied, he was a PhD student in the group.
Is it Geoffrey Hinton?
No, Geoffrey Hinton, but it's good that you bring up these names. Geoffrey Hinton is, no, he's more in neural networks, and then later neural networks, deep learning, deep belief networks, and so on. So he did a lot of things, but I'm currently looking it up. Let me get into this because that's also interesting. Because from my perspective, that's also one of the really few really original contributions. Vapnik, sorry. Vapnik, so V-A-P-N-I-K. When we talk about support vector machines, we will talk more about him. So he has developed basically the theory of support vector machines already in the 60s, but in Russia. And then after the fall of the Iron Curtain, there was more integration of this Russian knowledge about knowledge into Western culture, if you want. And I'm just currently seeing that you are chatting back and forth, so I can see your chat. So that when definitely in kind of Western computer science departments and so on, support vector machines really took off, and with Vapnik in the 1990s. And then in the 2000s, kernel methods, which are associated with the name of Bernhard Schulkopf, were popular. Also, variational inference started more and more. So this is when basically I also kind of got into the machine learning, not into the machine learning field, but when I first became aware that there is something like machine learning, which was actually at a time when neural networks were not popular. So maybe I've told this story to many of you before, but so when I in 2005 played around with neural network toolbox in MATLAB, the people in Tübingen, so other PhD students and so on, they kind of chuckled and so neural networks. Nobody uses neural networks for anything. It's very old school. And then I was completely discouraged in doing anything with neural networks. And then only 7 years later, backpropagation was again introduced specifically in the relation with convolutional neural networks. And then this kind of third, depending on how you count, if you count this as the first wave of neural networks, this is the second wave of neural networks, and this third wave of neural networks, or the second rediscovery of backpropagation, started in like the 2010s and is now known as deep learning because it sounds more fancy. So that's kind of the historical or one historical perspective. Anything you guys want to add or ask? Because the next thing will be talking about Michael Jordan. Any machine learning things that you have heard about that don't fit here or that somehow you want to add?
Yeah, actually, I was wondering one of the differences between statistics, classical statistics and machine learning, and one of the ultimate differences, I think, is machine learning focuses on the prediction over explanation to me. I mean, I came across some studies, and one of the problems of psychology, for example, is trying to understand and explain behavior without prediction. Do you agree with this?
Yeah, unfortunately, I don't. I wouldn't fully agree. So first of all, you can. So I know that people talk about this. So I would also, I mean, so I'm aware of these kind of things, and this is a typical thing that one can also, of course, then state. So that machine learning focuses on prediction, whereas statistics focus on explanation. There is this guy Danilo Bjok, who thinks he's the greatest person ever in terms of data analysis in neuroimaging. He has written in Neuroimage also a couple of comments in this regard. So pointing or trying to dissociate the statistics and machine learning and emphasizing the power of machine learning tools and so on. The reason why I don't fully agree with that is the following. First of all, you can do prediction with any kind of statistical method. So, maybe let's first address this term kind of prediction. If prediction means you learn parameters, and then based on these learned parameters, you predict what new data looks like. And then you try to kind of optimize your model in a way that it does good prediction. You can do that with anything that you would call statistics, specifically Bayesian statistics. So, for example, because for example in Bayesian statistics you always have these predicted data distributions that you get from integrating out parameters. So from this pure technical viewpoint, you can use statistical methods, so statistical models, which are essentially the same models as machine learning models for prediction. That's kind of the technical viewpoint. The other point that also is quite strong, and where also Wapnick puts in quite a lot, and where also in a way neural networks play a role, is in terms of the connotations you give to your models. And there, if one wants to, although I don't really find it helpful, but if one wants to, one can think in terms of, in machine learning, you want to make good predictions of data without caring about whether the models that you use has any resemblance internally to the actual generative process. So this is the strong case on statistical learning theory made by Wapnick. So if you the aim there not being to create a model of the world that is kind of mimicking the true generative processes, but just a model of the world that makes predictions as does the true generative process. Although I would have to say there that, first of all, I don't see, like, classical statistics also definitely does not try to make a nice model of the world. I mean, we did the GLM with the design matrix and the beta parameters. It's not aiming for a nice model of the world. It's just a linear model. So the Wapnick statistical learning theory pushes at this point. The reason why, from a scientific perspective, so I'm not somebody who's promoting machine learning or statistics. I'm a cognitive neuroscientist, and as a computational cognitive neuroscientist, to be precise. And I'm of course interested in scientific models of the world and use inference techniques from statistics or machine learning to create interesting models of the world. So for me, this purely predictive aspect, where which you, for example, can achieve with neural networks because they are just universal function approximators. Yeah, it's nice, but it doesn't provide scientific insight. Statistics, so old school statistics in terms of linear models, also doesn't provide that. Yeah. So again, there, in terms of prediction or the internal workings, neither actually achieves that. So this is why, in terms of this distinction between machine learning and prediction and statistics and explanation, I can't really agree with that, because the typical statistics that you learn also doesn't provide any interesting explanation. It's a linear model. So that's my long take on that. But I know that people.
Thank you for your answer.
You're welcome. But I know that that people make this distinction. This is the problem. Why I really would have liked to have started with something like that I really believe in, but where I can say, okay, machine learning is really this, but I don't believe in any of the things that I see. Okay, so maybe also to back that up, because it's if you read Introduction to Machine Learning and you see these papers that try to make the difference between statistics and machine learning and so on, it might sound a little bit weird what I'm telling you here. So I'm trying to backing that up, and of course also show you a little bit where this kind of line of thinking comes from. So that's Michael Jordan, not the basketball player, but the machine learning professor, who actually also studied on psychology, like many people in machine learning. He's at Berkeley. He has written a lot on graphical models, Bayesian Inference, and everything in machine learning. And he's very experienced. He was born in 1956, so he's more my parent generation. He has, and this is what I really like about him when he talks about machine learning, he has kind of a realistic view, because it's really hard at this point, specifically with the hype in artificial intelligence. A lot of people talk about machine learning and artificial intelligence and want to emphasize that it's the coolest thing ever and so on. And you have all this hype, and then it's really hard to filter through what is actually valid, and then and what is kind of trying to sell something, and what is actually the core and what is actually going on. And he has a very relaxed way of basically focusing on what is, and not kind of some fancy things. So there is this fireside chat, which you can have a look at. He has, I also want to point out this magazine, so that's the Harvard Data Science Review, and he has a nice article in there from last year on artificial intelligence. The revolution hasn't happened yet, where he tries to put the hype of AI into perspective, because, and this is the thing with the hype in AI, the only thing that happens with this hype in AI is that things that were going on in machine learning for the last 20 years suddenly became known more in the public. And suddenly it was this big thing. But for anyone who, like him, who was had worked in AI and machine learning for a long time, nothing really had changed. This is a very nice piece. This piece is actually based on a I wouldn't say it's based on, but it's fairly related to a Reddit post that he wrote up in 2015, and I would like to play that to you. So I've also put that into the references, but wait a second. I need to. I stop sharing for a second. Interesting. How do I get here? I made an audio of it because I didn't want to now read that to you, but give you an audio.
I am the computer voice of a Reddit post by Michael Jordan.
So can you hear something? Can you, so I'm starting it, maybe just check whether you can hear something. So if you hear something, say something.
Different collections of people, that is, academic communities.
Rasmus, can you hear something?
No.
No. Well, we can do it differently. Maybe I do it this way then. So apparently, I'm trying to play it here on. Has anyone played something and then shared it via Cisco WebEx? Otherwise, I will just play it out loud here and send and put it on the mic.
I am the computer voice of a Reddit post by Michael Jordan from 2015.
Okay, so I'm trying that again. I mean, you can, of course, if you don't wait, maybe. Multimedia, but I don't have a URL. Or a URL. Share browser, share content. Maybe I play it here. So it's even worse than doing audio in PowerPoint. I really want to play that now.
Apparently you have to click on, if you click on share content, you first have to click on optimize for motion and video.
Share content and then optimize for motion video. Okay. Let's try that again. Optimize for motion video. Okay.
often tend to have different applications.
Can you hear something now?
Yes.
Okay, cool. Thank you. So I'm playing you that now. So this is, you also find the text in the references, but this is what Michael Jordan says about this whole machine learning statistics question. So let's just listen to it. Whoa, now my video goes crazy. Anyway, there we go. Hasn't started, now it's starting.
I am the computer voice of a Reddit post by Michael Jordan from 2015. For fanciness, I have a British accent. I now take on the role of Michael Jordan. Personally, I do not make the distinction between statistics and machine learning. Also, I rarely find it useful to distinguish between theory and practice. Their interplay is already profound and will only increase as the systems and problems we consider grow more complex. Think of the engineering problem of building a bridge. There's a whole food chain of ideas from physics through civil engineering that allow one to design bridges, build them, give guarantees that they won't fall down under certain conditions, tune them to specific settings, etc. I suspect that there are few people involved in this chain who don't make use of theoretical concepts and engineering know-how. It took decades, centuries really, for all of this to develop. Similarly, Maxwell's equations provide the theory behind electrical engineering, but ideas like impedance matching came into focus as engineers started to learn how to build pipelines and circuits. Those ideas are both theoretical and practical. We have a similar challenge. How do we take core inferential ideas and turn them into engineering systems that can work under whatever requirements that one has in mind, that reflect assumptions that are appropriate for the domain, that are clear on what influences and what decisions are to be made, that can allow interactions with humans, that scale, and that are easy to use and are robust? Indeed, with all due respect to bridge builders and rocket scientists, etc., but I think that we have a domain here that is more complex than any ever confronted in human society. I don't know what to call the overall field that I have in mind here. I think it is fine to call it data science as a placeholder. The main point is that most people who I know who were trained in statistics or in machine learning implicitly understood themselves as working in this overall field. They don't say, I'm not interested in principles having to do with randomization, with how to merge data, or with uncertainty in my predictions, or with evaluating models, or with visualization. Yes, they work on subsets of the overall problem, but they're certainly aware of the overall problem. Different collections of people, that is, academic communities, often tend to have different application domains in mind. That makes some of the details of their current work look superficially different. But there's no actual underlying intellectual distinction, and many of the seeming distinctions are historical accidents. I also must take issue with the phrase machine learning methods. I have no idea what this means, or could possibly mean. Throughout the 80s and 90s, it was striking how many times people working within the machine learning community realized that their ideas had had a lengthy prehistory in statistics. Decision trees, nearest neighbor, logistic regression, kernels, PCA, canonical correlation, graphical models, k-means and discriminant analysis come to mind. And also many general methodological principles, for example, maximum likelihood, Bayesian inference, bootstrap, cross-validation, and expectation maximization. And of course stochastic gradient descent, whose prehistory goes back to the 1950s and beyond. Of course, the statistics community was also not ever that well defined, and while ideas such as Kalman filters, HMMS and factor analysis originated outside of the statistics community, narrowly defined, they were absorbed within statistics because they're clearly about inference. Similarly, layered neural networks can and should be viewed as non-parametric function estimators, objects to be analyzed statistically. In general, statistics refers in part to an analysis style. A statistician is happy to analyze the performance of any system. For example, a logic-based system. If it takes in data that can be considered random and outputs decisions that can be considered uncertain. A statistical method doesn't have to have any probabilities in it per se. Consider computing the median. When Leo Breiman developed random forests, was he being a statistician or a machine learner? When my colleagues and I developed latent Dirichlet allocation, were we being statisticians or machine learners? Are the SVM and boosting machine learning, while logistic regression is statistics? Even though they're solving essentially the same optimization problems up to slightly different shapes in a loss function. Why does anyone think that these are meaningful distinctions? I don't think that the machine learning community has developed many new inferential principles or many new optimization principles. But I do think that the community has been exceedingly creative at taking existing ideas across many fields and mixing and matching them to solve problems in emerging problem domains. And I think that the community has excelled at making creative use of new computing architectures. I would view all of this as the proto-emergence of an engineering counterpart to the more purely theoretical investigations that have classically taken place within statistics and optimization. But one shouldn't definitely not equate statistics or optimization with theory and machine learning with applications. The statistics community has also been very applied, it's just that for historical reasons their collaborations have tended to focus on science, medicine and policy rather than engineering. The emergence of the machine learning community has, inter alia, helped to enlarge the scope of applied statistical inference. It has begun to break down some barriers between engineering thinking, for example, computer science thinking and inferential thinking. And of course it has engendered new theoretical questions. I could go on, but I stop for now.
So the point being that Michael Jordan is of the opinion that there is no fundamental difference between machine learning and statistics, and that this whole field of essentially analyzing data and building algorithms and machines essentially that can deal with data and allow and help decision making, that this basically is like what happened with building bridges and physics, or building rockets and physics, and that this new kind of big field that goes from a very theoretical, pure mathematical stuff to the application in engineering kind of a style where you build something that solves a specific problem, that this is one big field, and that he would call this field data science for now. And this is also the point he makes in this article. But what I like about this Reddit post is obviously that he says things like that he doesn't think that these are meaningful distinctions. Good. So that's the Reddit post by Michael Jordan. I would suggest we take a break now, and after the break, I tell you then as an overview, and or we go a little bit. Let's say we go a little bit deeper into machine learning and content of machine learning. So what are we going to discuss in the summer term? So let's maybe also postpone questions to after the break and continue kind of 9:05 with the second hour. Okay, so this first hour was basically meant to transport the message that it's not that easy to make a clear distinction between statistics and machine learning, and that they are essentially the same thing. And I would just call the whole thing kind of data science. You build models to explain data, you estimate these models, or you learn or you train these models, and you evaluate these models. However, of course, there is a little bit of a difference in terms of the canon of methods that is usually being taught under the label of statistics and under the label of machine learning. And so now I would like to go a little bit more then into the question of what topics we should, which are typically discussed under machine learning, and which we would then also discuss this summer term and why. So in terms of topics and in terms of the question, what are the topics of machine learning? From my perspective, the topics of machine learning are the topics that you find in books that on their covers say machine learning. So by definition, if there's a book that says machine learning or introduction to machine learning and they discuss certain topics, maybe even things like linear regression, then apparently linear regression is a machine learning method. To kind of be a little bit inspired or to tell you a little bit of where my view on machine learning methods and the canon of machine learning method comes from, I want to first let you know about these machine learning summer schools. So I did my master in Tübingen, and I also in neuroscience. But of course, there has always been quite a strong machine learning community in Tübingen, with which I then also had different interactions. And I then also joined the machine learning summer school, so the MLSS, in 2007. What I didn't know actually at that point when I joined the machine learning summer school is that it was only the fourth or so of these summer schools, because they started only in something like 2002. So it was quite early on in this summer school kind of history. And what did I find there? So basically what I found were... Can you not see slides? Who sees slides?
I think you may have to go back to optimize for text and images.
Actually, I did that.
Okay.
Maybe I go back. I try to do that again. Can you see them now?
Yeah, now it's working.
Okay. Very good. So yeah, just always shout because I can't really monitor everything. In 2007, there was the machine learning summer school in Tübingen, which I joined, and what I saw there were topics as follows. So there was stuff on kernel methods by Alex Smola and Bernhard Schülkopf. There was stuff on graphical models by Zubin Garamani. There was something on Gaussian processes. Optimization, so Vandenberger was there, talked about optimization. There was stuff on statistical learning theory in the Vapnik sense by Olivier Bousquet. And there were things like Monte Carlo methods, so MCMC. These are actually the video lectures. So if you want to look at video lectures in machine learning, Google machine learning summer schools, and you will see that. What you actually don't see here as a topic in machine learning are actually neural networks, because as I said, at that time in the 2000s, neural networks were not really of interest to anyone. So what we can take from this is things like kernel methods, which are closely related to support vector machines, optimization, R and MCMC are topics in machine learning. Also Gaussian processes are topics in machine learning. This was the machine learning summer school then 2 years later, which happened in Cambridge, and was organized by Christopher Bishop, who also wrote a very good book on machine learning and pattern recognition, which I became aware of in 2007. And this was kind of the speakers list there, and the topics. So there was Bayesian Inference, graphical models, which are probabilistic models, information theory, MCMC again, kernel methods. There then also reinforcement learning shows up, Gaussian processes again, optimization again, a little bit on cognitive science. And one thing with deep in it by actually Geoffrey Hinton at that time, but in terms of belief networks, which are also Bayesian methods. So again, there was nothing that would really be called neural networks, but these kind of topics were taught at this machine learning summer school. And then 10 years later, at the machine learning summer school, we kind of find similar topics, but then at this point, deep learning has joined. So that's now definitely also a topic. And there's a little bit more on reinforcement learning. So this knee guy, so that's kind of the guy, the DeepMind guy on reinforcement learning and deep learning. And so this is just from last year, the topics that are being discussed at the machine learning summer school. It has Bayesian Inference, it has something on optimization, it has deep learning, it has reinforcement learning, Gaussian processes, it still has kernels, MCMC, has something on speech processing, so Arthur Jacobs will also be happy. Yeah, and other things that you can see here. So this is kind of if I wonder, so what is machine learning about? I usually check things like NIPS or the machine learning summer school or other conferences in machine learning to check out what people are currently talking about in machine learning, because that seems a field that is somewhat volatile and which is even more prone to hypes than our own field, where a lot of things always coexist. And yeah, but there are some things that show up again. And based on this, and of course, yeah, a little bit my personal preferences, plus the need to kind of make it a little bit kind of coherent. I came up with these topics for the machine learning course for neuroimaging. So today we're doing this introduction, obviously, and then the first thing that I want to talk about is optimization, because we will basically need optimization in many of the more specific methods that we then talk about. So this is kind of the introduction. Optimization are kind of the first part of the course. Then we will talk about something that is kind of always specifically in classification in machine learning treated in a way as a pre-processing step. You can also view this as a whole field of its own. It's a little bit hard to discuss it without going into the details. So we will talk about principal component analysis. I also had independent component analysis on there. So that was the next thing after principal component analysis. The thing with independent component analysis, which you also know from EEG and for eye movement correction, is the standard way to talk about independent component analysis is really confusing. So I decided to put in ICA or put ICA into the bigger context of static Gaussian state space models or static Gaussian models. However, this I'm starting a little bit from scratch, so I put it down here where it also fits in because it's going more into the probabilistic setting. Maybe I'm quicker, and then we can actually swap that around so that we first talk about principal component analysis as a basic feature selection method, and then independent component analysis in the context of Gaussian static Gaussian models already in the fourth week, because in a way, of course, ICA relates quite closely to PCA, but also not quite, and specifically in this setting, talking about it probabilistically is then quite different from PCA. All of this will hopefully make more sense if we actually go into the details. So these are kind of feature selection method, principal component analysis, something that you often will hear in terms of dimensionality reduction. ICA as something that was kind of popular in the 80s, 90s, blind source separation techniques that currently you don't see that much. You still find them in the machine learning books. As we've seen, we didn't really find them at the machine learning summer school, but this is the reason is that they kind of made their way more into the data pre-processing aspects. And then once we have kind of these pre-processing techniques, PCA discussed, then we will go into this big part of machine learning that I think most people understand as machine learning, namely classification. And there we will go in a way from, I don't know, simple to complex if you want. So we start out with linear discriminant analysis and logistic regression, which are very basic classification methods, but which allow, first of all, to spell out the relation between machine learning techniques and more statistics techniques, specifically, for example, in LDA, which is very close to GLM analysis, and then logistic regression, which is fairly close to neural networks. So once we have logistic regression, then we're going to talk about neural networks, which are today called, so in today's world, are called deep learning. But my point here is that deep learning is neural networks. And so there's basically no difference. So we will talk about deep learning / neural networks. Sorry, once we have done that, we're going to talk about support vector machines, which in a way similar to neural networks, but which are kind of a little bit different in terms of the optimization methods that are of interest, and then kind of make their way towards kernel methods, which are still around. So that's support vector machines. And then we go again more into advanced probabilistic methods. Either we do that then, or we have already done it. But then the last thing to discuss is variational auto encoders, which is the name given to variational inference these days, and also to the connection between variational inference and neural networks. So, like Michael Jordan said, the machine learning community likes to mix and stir things and put things together. So they really like that. They not necessarily then always check whether all of this, what they put together and so on, makes so much sense from an optimality standpoint, but definitely they mix together things a lot. And what they mixed together in 2014 was variational inference in neural networks, and this now exists under the label variational autoencoders. And this is what we're going to then finish on. So yeah. So for me, that's a kind of so that's what I can offer. Is there anything that you maybe I should first say reinforcement learning I still don't view really as a machine learning technique, but I view as an artificial intelligence technique. So reinforcement learning I will not discuss. For that, because that opens a whole new kind of bottomless pit. So maybe if I continue teaching at SCAN, there will be at one point this computation cognitive neuroscience course where we will do that. We have some stuff now also online on agent-based behavioral modeling, which relates to that. So if you're interested in that, I would recommend that. The other thing, if you're really interested in reinforcement learning, and it's by that meaning Markov decision processes, partially or observable Markov decision processes, and things like maybe even deep reinforcement learning, so putting this together with neural networks. Let me know. This is something you can happily do as a master thesis. But I don't see reinforcement learning at this point as part of machine learning. Another thing, another labeling thing that you might have come across is this notion of supervised versus unsupervised learning. One can give these labels. So PCA and ICA are usually referred to as unsupervised learning, and these classification methods are then usually referred to as supervised learning. So we will cover unsupervised and supervised learning in the course. Yeah, then beyond, another thing that we're not doing is Gaussian processes. We could, but we don't. MCMC we covered in statistics for data science. So if you're interested in basic MCMC stuff and approximate Bayesian computation, if you want, have a look at what we've done in statistics for data science in the last term. Any other thing the way I can reference you? No. Yeah, is there any other topic that you thought you would learn in machine learning? And maybe I can tell you where you can learn about it if we are not talking about it. So anyone who has anyone with their favorite machine learning algorithm, which we are not covering. So is there something that you can think of that you have in mind?
I have no algorithms in mind, but I assume that we will be a bit introduced to Bayesian inference, because you said there's so much Bayesian going on.
It's a good point. So Bayesian inference will be, so variational inference is Bayesian inference. So if you want to understand what variational inference is, when we're discussing variational autoencoders, I first will have to give some introduction to Bayesian inference, because variational inference builds on Bayesian inference.
Okay.
Yeah. Anything else? Also, but time also regarding a more kind of statistics-based introduction to Bayesian inference, and maybe even a little bit more profound than we will be able to do there, you find in statistics for data science. So because so in machine learning, it's a little bit the case that one starts kind of with probabilistic modeling and doesn't really discuss the statistics, the Bayesian statistics per se, which one can do. It's then still Bayesian inference, but it's not kind of Bayesian inference from first principles like you would do it in statistics. So if you are kind of interested in Bayesian statistics, not Bayesian machine learning statistics, then have a look at the statistics for data science course, which you also find from my website. But we will need to do an introduction to Bayesian inference. Otherwise, there's no way to talk about variational autoencoders. Another thing is actually, and with respect to Bayesian inference and machine learning, is that today, so there was, so in 2006 and so on, and with Christopher Bishop, there was a hype of Bayesian inference in machine learning. This hype of Bayesian inference in machine learning is currently not happening. So currently people talk about variational inference without saying anything, oh, this is very Bayesian. And all the other people who are not doing probabilistic modeling in machine learning right now, so all the deep learning people, so neural networks, this is actually not Bayesian in any case. So this is not even probabilistic modeling. So in a way, the kind of big interest in Bayesian inference in machine learning is currently not happening. So it's a little bit over right now. It's all very weird, but that's the Bayesian story. Okay, any other methods, topics? Good. So then to finish this section, and then also to relate the machine learning to what you are actually studying in the neuroscience, the last part of this introduction. So first, kind of a summary, what is machine learning? And this kind of summary is my kind of personal summary, so take it with a grain of salt, but that's really what I think about machine learning. So from my perspective, machine learning is bad statistics in the sense that it's usually not theoretically grounded. So this is also a point that is very strong in the Efron-Hastie book. It's not so much the point that Michael Jordan makes, but it's the Efron-Hastie point, is that in a way, it's also the Michael Jordan point, because he says that they didn't really develop new principles, but they mixed together things. And so the machine learning is kind of an algorithmic approach that let's do something, let's figure out, let's put something together, and let's worry about the theoretical underpinnings of what we're actually doing here later. So in this sense, machine learning is bad statistics, because statistics is already mathematized machine learning. So at one point, of course, the things that were done, and You see that if you read things, the things that were done were just proposed as kind of more like algorithms, like for example ANOVA. For a long time that was basically putting together some formulas, and then only later the whole theory of the GLM was basically put around it, or this whole thing was embedded there, and then it made more sense. But it started also from a more kind of machine learning algorithmic thing. Then this is also in a way what Jordan says. So the thing is that machine learning, and this is sometimes actually, this makes things a little bit hard sometimes in machine learning, is that it's often done by computer scientists, and computer scientists don't have, they're a little bit like physicists, they don't have a very kind of formal mathematical training, and they also don't have a real statistical training. So they discover that statistics has some methods to learn parameters of models, and then you see basically statistics through the lens of computer scientists. That's, for example, how I studied Bayesian inference, that I always saw Bayesian inference kind of in the machine learning books as explained by computer scientists. And then at one point I figured that if I actually go to the original sources on Bayesian inference, so kind of 60s, 70s Bayesian statistics, Lindley and Savage and so on, Definetti, that things make more sense. So in a way, machine learning is kind of statistics as communicated by computer scientists. For a lot of people, machine learning seems to mean classification. So whenever it's about face recognition, that's machine learning. So, and these are usually classification algorithms. So that seems to be a case. From my perspective, the original things, this is also what Jordan said. He said certain things originated out of the statistics community. Again, always Kalman filter or hidden Markov models, but they are really kind of statistical models. But support vector machines and neural networks, which are these probability-free classification algorithms, if you want. From my perspective, if machine learning wants to be its own field with its own method that only were developed in machine learning, then I would say support vector machines, neural networks are really, really machine learning. Then you have this other problem that now everything is called AI. And my bottom line is, just call statistics and machine learning, plus things like, I don't know, data organization, data ethics, and so on, just call that data science. So, I think I will also try stop kind of differentiating statistics and machine learning, or pointing out parallel things between statistics and machine learning, because it's all just the same thing. And if you read one statistic book from start to finish and a machine learning from start to finish, then you actually would see that it's the same thing. If you only read the first 20 pages in either book, then you might think that they are different things. But if you read the full thing, then you see that it's the same thing. Talking about books, this is some recommended reading, where I actually also encourage you to read the chapters that on the topics that we discuss. I kind of show them here in terms of how much I recommend them in a way, but also in terms of how complex they are. So if you want a kind of light introduction to machine learning, I think this relatively new book by Ian Goodfellow, which is called Deep Learning, is nice. Of course, there is a little bit of a focus on deep learning, also neural networks in there. However, in the later chapters, in kind of one of the last chapters, they also discuss variational inference. So it's kind of it's an introductory text to machine learning, which I think is useful, but I don't feel quite satisfied with, but that's just me. So have a look at that. So you find all of these books, of course, in the reference folder. Then there's this introduction to machine learning, which doesn't have this strong bias towards neural networks. It's good. It's the mathematics are sometimes a little bit light, so you don't really know how to implement things then, but it's definitely also a nice introductory thing. Then Pattern Recognition Machine Learning by Christopher Bishop. That was the book that really got me started on machine learning methods. It covers a lot of ground. It has a quite strong Bayesian, it has a strong Bayesian flavor in the sense that Christopher Bishop really pushed to use Bayesian inference in machine learning. It's good, so especially the introductory. So the first part of the book is quite good, although sometimes it references parts later in the book, and then it gets a little bit confusing. The later parts in the book, where the more advanced stuff is discussed, is okayish. Then at one point it gets a little bit short, and then it's not really that clear anymore. So the book that I recommend most is this book by Kevin Murphy on machine learning. But of course, this is really a perspective on machine learning, namely a probabilistic perspective. And he actually also discusses certain things that relate more to classical statistics in there. So he might actually discuss things like t-tests also. But this is really like a profound, comprehensive book, and at parts actually clearer than the Bishop book. So these are all books that I recommend. But you find millions of other texts on machine learning. But to really get to get into the subtleties, I recommend these two latter books, and to get a first overview, I recommend these other two books. Anyone else recommending a book that they came across? No. Good. So now to something completely different, namely neuroimaging. So the question is, why do we talk about machine learning in statistical methods in this Master for Social, Cognitive, and Affective Neuroscience? And the reason we're doing this is, of course, because machine learning methods are being applied in cognitive neuroscience data analysis, and specifically neuroimaging data analysis. And I focus here on fMRI data analysis. Of course, machine learning methods like classification are also being used a lot in EEG data analysis. So this is a slide I think all of the SCAN students should be familiar with, because we've seen it in our introduction to neurocognitive methods. And so please remember that fMRI data is acquired over time and space. So you have voxels and you have MR signals over time. And we've seen earlier on, specifically, we've seen a very similar thing in EEG, that one can analyze such data in an event-related manner. Of course, if you now replace fMRI data by EEG data, where space means electrodes and the signal is potential time series, then of course you all are aware of different event-related potentials, which are just event-related averages. So you know what that is. This is obviously what we've discussed. So whole brain mass unit JLN, this is what we discussed in the winter term. Then there is something looking into connectivity analysis and doing biophysical modeling, which is something you will find me talking about on YouTube, because we did summer terms like that in the past, but we are not doing that now. But what we are talking about in this summer term is essentially what in neuroimaging, and specifically cognitive neuroimaging, functional neuroimaging, is called multivoxel pattern analysis. So multivoxel pattern analysis, this is the most prototypical application of machine learning methods in neuroimaging. And I want to briefly talk you through an MVPA analysis, so that you know how machine learning methods, specifically classification methods like the ones that we will discuss, namely neural networks, support vector machines, logistic regression, linear discriminant analysis, possibly with some pre-processing using PCA or ICA, how this is applied in neuroimaging. Has anyone of you presented an MVPA paper? Just say yes or say what this was about. No? Nobody has discussed an MVPA paper? Good. Did Timo tell you about MVPA? Is anyone still there? Where are my participants? So no MVPA for anyone so far. Interesting. Okay, so let me tell you then about MVPA. So the basic idea of MVPA is kind of brain reading. So the idea is that you present a participant. It's a typical thing in vision science. You present participants with different kind of stimuli, for example, 2 different categories. So you show people images of bottles and images of shoes. And while you show them these, like in a standard functional neuroimaging experiment, you record fMRI data, and then you focus either on the entire brain or a certain subregion, for example, a region of interest, and you extract the data from these voxels. These voxels are then called features. They are then the features of a machine learning algorithm. And then, so you extract patterns. So you're looking at multiple voxels at the same time, which are shown here. So you have multiple voxels, and these gray values are supposed to indicate the level of activation of a given voxel. So here there are 6 voxels. The level of activation when the participant viewed bottles and when the participant viewed shoes. So you can see if the participant viewed bottles, these upper voxels are a little bit more active, and when the participant views shoes, these lower voxels are a little bit more active. And then you take data like this from, let's say, 2 runs, and you train a pattern classifier to associate with these labels, with these feature vectors, the labels of bottle and shoe. And then once you have trained the classifier, you present to it a new pattern from something that you left out, and you ask the classifier, is this pattern that I'm showing you now, is this more reminiscent, or does it remind you more of a shoe or of a bottle? And then you get an answer, and you can average and because you know what the participants saw when this test feature vector was recorded, you can then to a certain accuracy infer what the participants saw, and you can summarize this as a classification accuracy, which of course, if the classifier is just guessing, it will have a classification accuracy of 50%, and if you find something higher accuracy than 50%, you can then say, okay, apparently these voxels encode some information about the external stimulus. So what you're actually doing there is basically to test the statistical association between the stimulus and a voxel pattern, but you're doing it in terms of, if you want now, prediction, not by you also estimate the parameters, but then you don't do parameter inference, but you use your learned parameter as to compare that with a novel pattern. And this made headlines around 2005, also when I got into neuroimaging, because this was applied, for example, by John Dylan Haynes, but also by Frank Tong in the context of attention and, essentially of attention, and in terms of, this thing when you only see one thing at a time. Rasmus, what's the name? this thing when you're aware of something, and then for a certain time, and then so like the Necker cube. What's the name of that? When you are aware of something, and then you're nobody.
Salience?
No, this thing where you are conscious of something at a certain point in time, and then at a later point in time, you're conscious of something else, because binocular rivalry. That's the point. Binocular rivalry, where you get presented as one stimulus to one eye and another stimulus to the other eye, and then at some time you are aware of the one stimulus, at other times you are aware of the other stimulus. And of course, this kind of awareness thing is something subjective, and but people can indicate of what they are currently aware. And then they showed that they, in 2005, John Haynes and so on, they showed that the patterns in visual cortex co-vary with what people are aware. And this is why at that point, machine learning methods in neuroimaging became really popular. There's a paper that I also put into the reference folder, which is called, which is by Cox and Savoy, which was from 2003 in neuroimage. Which basically does the same thing here. So it uses this MVPA logic, but they didn't really make headlines. But then the Frank Tong and John Dylan Haynes paper, which were related to awareness or attention, they really made headlines. So this is when machine learning, if you want, became popular in neuroimaging, because until then in neuroimaging, so from 1990 to 2005, it was mainly GLM, and then a little bit of DCM, some connectivity, also some multivariate things like PCA and so on. But this classifier approach, this multibox pattern analysis approach, then really became popular in 2005. And because it became popular, I, of course, also wanted to do something like that. And so this is my second fMRI project. So the first fMRI project, no, it's actually my third fMRI project. So the first fMRI project that I worked on is a paper by Lee and Ostwald, which also uses classifier MVPA analysis for fMRI data. That was really my first fMRI thing. Then I did something on multisensory integration, doesn't matter. And then I did this. So this is a classical vision science MVPA paper, if you want. So what we were studying there is the processing of form in visual cortex. So we presented participants in the fMRI scanner with these patterns, which are called glass patterns. Glass because the guy who invented them using a Xerox machine or something was called glass. The point of these patterns is that you get this impression of global form based on local properties. You can also use Gabo patches for that, but at that point, for some reason, the person that I was working with didn't want to use Gabo patches anymore, but wanted to use these glass patterns or whatever. We use these glass patterns, and you can see that you here see kind of this concentric pattern, here you see kind of a radial pattern, here you see a translational pattern, and here you see a random pattern. And we presented these to participants and in the fMRI scanner, and then we mapped out their visual cortex. So here you see a flattened cortical surface, and you see borders between the visual areas, so V1, V2, V3, V3A. Then you see LO, so the lateral occipital complex, which is typically associated with object processing here. You see some areas that are activated by these glass patterns, which I then call glass pattern responsive regions. And this is the other hemisphere. So we wanted to know how well voxel activation patterns in these different regions can discriminate between these different stimuli. And the point is that these random stimuli, or that essentially all of them have very similar local statistical properties, but they have globally then different statistical properties in terms of the stimuli. And so the analysis that we did or the whole experiment that we did is that we presented these class patterns for 16 seconds, given class pattern type. So for example, concentric was then shown 20 different class patterns, but concentric for 16 seconds for one block, and then for 16 seconds the radial was shown, and then another block the random was shown, and that was repeated. Of course, the translation was also shown. And then we extracted the voxel signal activation from regions of interest. So these regions of interest that you see here, V1, V2, V3, V3A, and class pattern responsive regions, and LOC. So lateral looks a bit complex. And then the question is, then you have many voxels from each region. So we chose the 130 most activated voxels over conditions. We normalized each time course, and to account for the hemodynamic response, we shifted the data with respect to the stimulus by 4 seconds. You can also call this the Poorman's or the MIT-Man's hemodynamic response modeling. Then we averaged the data points in one experiment block so that we have kind of the prototypical activation pattern for a specific glass pattern type. And then we used a support vector machine for classification. So we then trained a support vector machine to associate with the fMRI activation patterns a specific glass pattern, and then we always left a certain run out, so how many runs did we have? I guess 8. So that we trained on fMRI data from most of the runs, but not on one run, and then used the trained support vector machine to predict what's happening in this remaining run. And then we averaged the accuracy across cross validations and did some statistical evaluation. So this is then a typical result from these kind of MVPA studies. So on the x-axis, you see here different visual regions, so V1, V2, V3, V3A, VP, V4, and LOC. And what you see are binary comparisons between concentric and radial glass patterns, between the random glass patterns and random and another random control. So there was another random control that we also did. And the point here is that for all these binary classifications, the chance level is 50%. And as you can see, we are a little bit above 50%, but there's essentially basically not much difference between classifying between random and concentric and radial. So somehow the presence of a larger or of a intermediate, let's say, a global form doesn't really matter. In early visual cortices, it gets a little bit stronger. So this presence of a global form makes a little bit more difference if you go to higher visual areas. And then definitely in LOC, you can much better discriminate between these global forms versus random glass patterns, meaning or implicating LOC using this approach in the processing of global form. Of course, it was known that LOC is answers or is responsive to objects and global form before, and this is essentially a different way to show that, and it was targeting a little bit this intermediate level. So obviously we didn't show bottles and shoes, but we showed these glass patterns, and that was what we could find there. And this is then something that I'm very proud of, because the question is always how many voxels should you use? And if you use more voxels, you usually get to some kind of, so if you for one region put in more voxels, you get to some asymptotic classification accuracy. So you have larger activation patterns, and some of this then usually behaves in some way asymptotic. It might go down, but in some way asymptotically. And the question is, if you just report these kind of classification accuracies, where it's a little bit like if you think about your TR measurements, where do you measure that? Do you measure that here, where there's basically no difference? Do you measure that here, and so on, and how do you quantify that? And here I proposed to just basically talk about how many voxels you need to achieve a certain difference in classification accuracy, and that was then lower in the higher visual areas than in V1, so that you basically that the kind of the neural code converges on fewer cells or fewer voxels in higher visual areas. Yeah, so that was my stuff in using MVPA. If you do these kind of studies, and if you, for example, are really interested in doing these kind of studies, these typical MVPA studies, then do a lab rotation or a master thesis in Radek's lab, so, or also Felix' lab. I think they use this for discriminating somatosensory stimuli. The thing is, once I worked on this for like these 2 years, so 2005, 2006, maybe 2006 to 2008 and so on, you feel that, yeah, it's nice, but can we do a little bit more, and can we make it more biological and so on? So you grow a little bit out of this, or at least I grew a little bit out of this, because after all, voxels are not biological entities. The whole thing is essentially just brain mapping, in the sense that you can say, yeah, this area discriminates between global form and this area doesn't, but you don't talk about new biological interactions between different areas and so on. So you definitely want to do a little bit more than these classifiers, which also then got me more into this dynamic stochastic models and so on. In any case, and of course there are these other things that you are starting to be more interested in, how these differences in activation patterns relate to parametric differences in the stimulus space, which then leads you down the road of what people call representational similarity analysis or multidimensional scaling. So this is kind of a very basic thing that people still do a lot, but it's also a little bit boring. I mean, it's like standard GLM studies. If you just do standard GLM studies all the time, you get horribly bored and you don't feel cognitively challenged. But yeah, so this is what I did early on during my late master's and early PhD time. Again, to point this out, how this now relates to the content of our course. So everything that we will do here in terms of LDA, logistic regression, neural network support vector machines, that's really things that are being used for these kind of analysis, so for MVPA analysis all the time. Optimization is actually what's happening in the software that one uses then for MVPA, and these other two things are kind of for voxel selection. So this is kind of the application of machine learning methods in neuroimaging. It's all about classifying stuff. It's closely related to MVPA. Yeah, in a way, that's the big link here. There is more to it. So, for example, if you talk about variational inference, then variational inference, which is a big topic in machine learning, is of course also the method that in neuroimaging you use for learning other more biophysically interesting models, so DCMs, for example. So there are many other links between machine learning and neuroimaging, but the most profound and the first link that comes to everybody's mind when you say machine learning techniques in neuroimaging is that people think MVPA, classifier. So, and this is what you then also should think, but then think more. Okay, so that was the last part of the introduction then. So then I would suggest we discuss questions now, and after that we take a break and start with optimization.